So we are in Unit 2 on the building blocks of matter, and we are now looking at the discovery of the electron. Now, the discovery of the electron is generally credited to J.J. Thomson in a very famous experiment that he published in 1897. And it was an experiment on what are known as cathode rays in a device known as a cathode ray tube, sometimes called a CRT. This is what we used to use to watch television. Now, before we had LCDs. So the basic idea in J.J. Thomson's experiment is we're going to have a cathode and anode now, but it's going to be in a high vacuum environment. And the way that this environment works is, there's going to be sort of like a large glass tube that I can do various electrical things within. There's going to be a cathode made out of some material in here, and I will hold that cathode at a very large negative voltage. And what I'm going to do is I'm going to try to coax these negative removable charges, if you will, out of the atoms that make up this cathode. And the way I'm going to coax these out of there is I'm going to apply a rather high extraction potential, which I will call V sub x, between that cathode and a metal screen in here, right, so that I can create a large potential difference in a strong electric field. And when you do this, you drive certain rays, or some effect comes out of that cathode. Now, the way the experiment's usually carried out, you want to what's called collimate the beam, so where there's going to be something called collimating slits. And these collimating slits, their task is basically to give you a well-defined beam of particles, because the particles, or whatever these rays are initially, they come out in all different directions. So the collimating slits usually would consist of a disc here with a horizontal slit, right, that only allows particles in along that one narrow line, and then you would have a follow-up disc with a vertical slit. So by the time the cathode rays have managed to pass through both of those, you have a nice, now well-collimated beam. The particles are coming out in a very nice straight line. Now, after they go through that straight line, the tube then continues along. It eventually then opens up into a nice large vacuum environment. And generally what you do is you take the front end of this vacuum tube and you coat it with some phosphorescent material. Phosphorus is a very good choice for that. And when you carry out the experiment, what you will notice is some kind of rays definitely come out of the cathode. And whenever you turn on this extraction voltage, you start to see a nice spot appear on that screen. So you can see you've got this nice, well-collimated beam. So the real question was, what is the nature or identity of these cathode rays? And Thomson carried out a very clever set of experiments to establish their true nature. The first thing that he established was that they were actually electrically charged. So they do seem to be some kind of charges that we can remove or strip out of the atoms in the cathode. They're some component, if you will, of those atoms. And to discover their nature, one of the first things you can do to see if they are charged is you can apply then an electric field to this beam by applying a deflection voltage, V sub D, right? And I will make this the positive plate, and the lower plate I will make the negative plate in my example. That then applies this nice constant downward electric field between those capacitor plates, and the strength of that field E is fairly easy to determine experimentally, because it's just going to be the voltage that you apply between the plates divided by the plate separation D. So I'll call this here plate separation D. Now, as soon as he did this, what he noticed was when the particles go through that electric field, they actually pick up some momentum and the beam deflects. And it turns out that the beam deflects as it comes through here, right, in an upward direction. So instead of traveling perfectly straight through to make our perfect straight spot after the beam, what we have is we are coming out then here. My sketch isn't so great. I'll try to improve the sketch a little bit. You can see the different trajectories. The beam then is now emerging at some deflection angle theta. So, some observations or results from this experiment. Well, one of the first results is that when you check all of the various signs here, we notice that the cathode rays are not only charged, but they travel like negative charges, right? They're trying to climb up these electric field lines. So the cathode rays are negatively charged. Great. So there's some kind of negatively charged component inside of the atom. The next question, of course, we want to do is to try to determine the magnitude of the charge. Now, so we want to determine the nature of these things, determine their charge Q. Well, to do this, there's an issue, though, right? We know the strength of the electric field that we are applying, and by looking at the deflection, we can figure out the force, and taking the force and dividing by the electric field, that should be able to tell us the strength of the charge. But to relate the amount of deflection to the force, you need to know something, right, about the initial momentum of these particles. Right? If they had a lot of initial momentum, they won't deflect very far. So you first, before you can determine Q, as a preliminary step, you have to determine actually the velocity of these particles. Now, to determine the velocity, Thomson came up with a very clever technique. The way he determined the velocity was by applying a magnetic field B that cancels the deflection. So, let's see how this works. In his case, he would apply then a magnetic field that goes into the board here at right angles to the electric field. And when you do this, and you know the velocity is in this rightward direction. When you do V cross the inward B, you find an upward direction. But, of course, the magnetic force is the charge times V cross B, and these we've already established are negative charges, so the magnetic force, it turns out, is downward. So if we tune the magnetic field just right, we can cancel out this deflection completely by leaving ourselves with no net force inside those capacitor plates. So, the basic premise then is that there is this upward electric force, F sub E, the magnitude of which is the charge on these particles, these cathode rays, times the electric field. Notice I'm taking Q and E to be positive values. I'm only worried about magnitudes right now. There is also then a magnetic force. Now, in general, the magnetic force law is QV cross B. In this case, getting that magnitude is fairly straightforward. It's the magnitude of Q times the magnitude of V times the magnitude of the magnetic field B. Also notice the velocity is at a perfect right angle with respect to the magnetic field. So yes, certainly there's going to be some sine theta, but theta is 90 degrees, and that sine theta then gives me 1. Now, if I tune this magnetic field into perfect balance with the electric field, then, as you can see, I can immediately solve for V. So when there is no deflection, that implies then a nice balance in this equation. That implies then that QE must equal QVB. Then the charges, of course, cancel, and I can determine uniquely then the velocity of these cathode rays as simply the electric field that I know by taking the deflection voltage and dividing by the distance between the plates, and then I can divide by the magnetic field, which I can also determine experimentally. So I've now determined the velocity V. That's perfect. That was the first step in relating the deflection to the angle. Now that I have the velocity, now I can determine the angle. that I would expect from this, the expected angle. Now, the geometry in the experiment, of course, is that, well, the trajectory as it travels between these parallel plates, right, actually is the arc of a parabola, which then turns the direction of the beam. But once it leaves that parallel capacitor plate where there's no more force, the beam then is going to travel, of course, in a perfect straight line. And the way the device is designed, this where this angle theta opens up, that actually makes up the largest part of this displacement. Right? We allow for a nice long distance between the deflecting plate and to the beam. So the deflection of the spot then really is telling us a direct measure of the change in the direction of the beam as we go across the final portion of the chamber. Now, to determine the change in direction, that means we need to know the velocity after the effect of the parallel plates. And to determine that velocity, we need to know the final momentum. Now, because momentum is conserved, this is going to be a pretty easy calculation, right? We have the initial momentum of the particle, which I will call P parallel, which is just the mass of these particles, which we don't know yet. So we see there's another unknown coming in here, but times the velocity of the particles, which is something that we know. And because the force, you will notice, is perfectly straight downward, there's going to be no change in that parallel momentum. Now for the perpendicular momentum, as you can see, there's an upward force, and its magnitude is Q times E. And so we just have to figure out, for this constant force, QE, how much change in vertical momentum am I going to pick up? How much vertical momentum will this thing pick up? Well, that vertical momentum, or perpendicular momentum, I will call P perpendicular. Well, it starts with zero momentum in the perpendicular direction. It then picks up a momentum, and we know the formula for momentum, right? Momentum is just force times the amount of time over which you apply the force. And in this case, the force we know is Q times E. Right? We don't know Q, but we know the electric field for sure. We're trying to relate these quantities. And the time that we spend between the plates, now that is something that we can now figure out, right? This is where that velocity comes in. We certainly know experimentally the length of the plates, which we will call L, as opposed to their separation, which we're calling D. We know the length of the plates, and we know how quickly the beam is traveling through them. So the time spent then is simply the length through which we're traveling divided by the velocity at which we are traveling. The final total momentum that then defines the velocity and the angle theta that we measure in the experiment, I'll call this P total, that's my final total momentum vector, is just the vector sum of these two perpendicular vectors. So now, to determine theta, it becomes a matter of trigonometry. The tangent of the angle theta, of course, will be the opposite side divided by the adjacent side. And we now know all of these quantities, right? The perpendicular momentum is QEL over V, and the parallel momentum was MV. And I can simplify this a little bit. I get, oh, this is interesting. I now know the charge to mass ratio of the cathode rays. I'm not able, apparently, in this experiment to separate out absolute value for charge or absolute value for mass. That will have to come later. But at least for now, I know there's a constant charge to mass ratio, and I can relate it to my angle theta. The remaining quantities that go in here are E times L, and then divided by V squared. I get two velocities here in my denominator. Now look at this, a quick check that we've done our calculation correctly. The tangent of theta is dimensionless, so I should have the same dimensions in my numerator as in my denominator. Now in the numerator, you will recall that electric field times distance always gives me a voltage, and a voltage times a charge always gives me an energy. So the numerator has units of energy. The denominator looks a lot like 1/2 mv squared, right? Which also, of course, is kinetic energy. So numerator and denominator have the same units. This is a properly dimensionless quantity. So finally then, I can solve for something interesting about these cathode rays. We know their charge to mass ratio, and I can solve for that by just dividing both sides by my remaining factor, which gives me v squared over EL times the tangent of the angle theta, which then relates the charge to mass ratio to all quantities which we can determine experimentally. Great. And here is the value that Thomson discovered for this. He discovered, when he does the measurements, that he gets a very interesting value. He gets 176 billion now coulombs per kilogram. You will notice that that is a much, much larger number than the charge to mass ratio of, for example, the lightest element, hydrogen, which is something that we can determine from electrochemistry experiments. So if you look at capital Q over capital M for the hydrogen ion that we can measure in electrochemistry, you may recall that that value was only 96 million coulombs per kilogram. Now, we can do something very interesting here. That's million, not billion. Pardon me. We can do something very interesting here. If we divide these two quantities to look at this rather large ratio that we are seeing, right? If I take the charge divided by the mass for the cathode rays and compare that to the charge of the hydrogen ion divided by the mass of the hydrogen ion, right? What I get is the charge ratio of the cathode rays and the hydrogen ion times the mass ratio of the hydrogen ion to the cathode ray, or to the electron, which is what we now know these are. Now here, when we make that division, you'll notice this number is very close to 0.1 billion. So when I make this division, 176 basically gets multiplied by 10. I get a value of about 1800. Now, why this is so relevant is that we have very good reasons to believe that because we are able to remove these negative charges from atoms, like metal atoms, right? When we do the electrochemistry experiments, we also have good reason to believe come with these unit removable charges. If we just make the assumption that these two charges are the same, or at least approximately the same, then we see, and in fact we have good reason now to believe they are exactly the same, that this ratio should be approximately, or actually for hydrogen is 1. We then have an immediate measure that the mass of the lightest atom, now remember, they did not know the absolute masses of atoms. They did not know that yet, right? But the ratio of the light, but they did know their relative weights, so they knew hydrogen was the smallest atom. So the mass of the smallest atom divided by these cathode ray units, which we seem to be able to extract, is really large. It's about 2,000. So this then led to Thomson proposing a model for what the atom must look like. So this is known as the Thomson model for the atom. It's sometimes called the so-called Plum pudding model. And the idea went something like this. Because it seems that the remaining piece of the atom that's left before you extract these negative charges, that positive portion of the atom contains all of this mass. There's good reason to think that those atoms must be rather large compared to the electrons. So in his plum pudding model, the atom consists of a large positively charged sphere. I'll put a plus on it, right? Large positively charged sphere, and he made a nice simple model of a constant charge density. So large sphere, radius r, well, large, I mean large compared to the electron. It's small. They didn't know how small the atoms were yet, but they had some, of course, basic size, which we call the radius r. And then he assumed, a rather reasonable assumption, that there's a constant charge density rho rho, which is going to be greater than 0, right? That makes up that sphere. And then the idea is within, let's say a large positive sphere, just so we're very clear. And then the idea is within that sphere you have embedded these very small negative particles, the electrons. And then this makes up the structure of the atom. So we've got the large positive sphere, small embedded electrons, making up the final structure for the atom. Now it's called the Plum pudding model because the basic idea is that this positive charge region, right, that of the atom is like the pudding that kind of holds the thing together, gives it most of its mass, but within it there are these little spots, these tiny little pieces of plum making up your plum pudding. So that's the Thomson model of the atom. It actually has some very interesting consequences. It can explain, for example, the fact that there are certain fixed vibrational frequencies and spectral lines that are observed for atoms. It also can explain in ways that other models we will see have difficulty with. It can also explain the fact that atoms are stable. They have a certain stability to them. And there's certain ways you can arrange charges in a mechanical equilibrium in these types of configurations with point negative charges embedded in a positive charge background. So that represents then the discovery of the electron. The next issue we're going to take up is, well, how do we actually get some absolute values on these things, right? It's nice that we know the charge to mass ratio on the electron, and the mass of the electron relative to the mass of the atoms. We know those ratios, but it'd be nice to have some absolute values on things. We have to find a way to get an absolute value for the mass of the electron or for the charge of the electron. And that is what we will take up next time.